Hi everybody and welcome to another video, and today we are going to take a look at the coding part of the last lecture I provided. The link is in the description, namely the NASA toolkit SPICE. Now for those of you who have not seen the last video, just a quick reminder or what is SPICE about. SPICE is, like, I would say, one of the most mighty tools NASA has ever provided. It's one of the oldest software also as well. And it helps you to determine and compute all geometric considerations and effects and positions and what have you in the solar system. So it doesn't matter if you want, for example, to compute the trajectory of a spacecraft to a comet, or the relative position between moons in the Saturnian system, or for example to see how a radio dish is pointing towards a certain object. All these kind of geometric considerations can be done in SPICE. And SPICE is very, very complex. There are like tons and tons and tons of functions based on something else called kernels. These are like the fundamental parts of it. And there are hundreds of them, thousands even. And of course, in the last years, I provided here some updates on my YouTube channel and some videos using SPICE, but not sophisticated overview of SPICE itself. And today I would like to start with this overview session, the coding part based on the theoretical slides from last time. However, a larger workshop is currently planned for the next semester for my students. You know where to execute these things and so on. I have shown you this in the lecture, but for everybody else watching this video, the link is in the description of the corresponding code. You can either code in parallel with me now, or just execute it cell by cell and check my video and hear my explanation what's going on. However, without further ado, I would say we are going now to Google Colab. This is the environment we will use for this video, and there you can simply follow it. You just need a Google account, and we don't need any GPU power or so. You just need the content I will provide to you now. And I would say also in the timestamps, you see the different lectures, the different sections. So if you're only interested into certain things, for example, the 3D visualization of a comet, we have the comet 67 Churyumov-Gerasimenko, then feel free to skip also the other parts. Every cell should be, not self-explanatory, but should work for itself. Maybe the very first part where we import all the libraries are important, and also the kernels. I would suggest to just download also the entire file just to be sure everything is working properly. Now, I would say let's go into Google Colab and let's start coding. Okay, very well. Let's start with the coding part. So what we will do first, of course, is we need to install SPICE and also other libraries that we need that are not per default installed in Google Colab. Now, first of all, we need SpicyPy, and we also need to pip install Plotly, because these are the things we need. Of course, SPICE on the one hand, and Plotly, we will use Plotly also for the 3D visualizations. Now, in the meantime, we can already start to import things. We need, of course, a date time, because we will work on some date time conversions. Maybe you know from last time, this ephemeris times and so on. SPICE is very, let's say, time hungry. We need glob, for example, as well, which is used to go through different directories to find certain files. Will be needed for the kernels. Now, the auto-completion is nothing I need now. Import Plotly as plt, numpy, pandas is also something we need. Looks very good, but we don't need express. We will later need graph objects from Plotly, and I will just import this as go. And finally, of course, import SpicyPy. Did the installation work properly? Yes, everything worked pretty well. That's very cool. So what we can do now here is we add now a first text block, and I would suggest we are computing Earth's position and velocity as our first project, as our first intermediate step in SPICE. Now I have something copy-paste. I will copy-paste something now that I already stored. It's namely 3 different kernels, and don't worry, I provide all the kernels also in the description. And of course, you can download the notebook as I just showed you. What do we do here? Now in Google Colab, I just did it here as well, we can escape the Python runtime by using an exclamation mark like here. In this case, here in the top part, we pip installed something, and here we use curl to download the kernels. So the kernels are here the HTTPS links, and then we will download them and create a directory if it's not existing. And in this case, it's called kernels/lsk, lsk, nif, and so on. So this kernel is a time kernel. This kernel here is a kernel that contains the position of the Earth for certain time ranges. And this kernel here contains some physical parameters and constants that we will need. In my last video, I explained all the details of these kernels, so I would refer to these ones if you are interested what this means. Now, if we go here, I have to be aware, I think, because I am in the lower left here, so I hope I'm not obstructing the view. So when we click here on the files, we see there are no files, but the sample data provided by Google. So if we just execute it, we will just wait for a few seconds, then it's downloaded, and we have everything here in our kernel directory. What's really important to know is that these files, they are stored temporarily. Yeah, so things will be deleted if you are not storing them somewhere else, for example, on Google Drive. Now, in the first step, what we need of course the kernel file paths, and the kernel file paths is something we can extract with glob. So glob, what does it do? Is we go into the kernels directory, and then we want to have all files from all subdirectories. Now in this case, it may appear as an overkill. But if you can imagine, if we have an automatic script that downloads several files at the same time, then these kind of commands are pretty useful. Yeah, so I can simply download it. I would also suggest to print the file path so that you see what is going on. Let's have a look. So we have here the 3 different kernels, and now with Spice, we need to load these kernels, and we do this with spicypy.furnish kernel file paths. So the autocompletion was pretty successful to understand what I wanted to do. So the kernels are now loaded, and what we can do now is we can now compute the position and the velocity of Earth with the kernels that have been provided. For this, I would suggest that we will take the date time, and we take date time now. So literally the time we have now, datetime.datetime.today. And this is a format, the datetime format. So what we need to do now is we need to convert it into a string format. So we can simply convert it. The autocompletion makes a suggestion. Let's have a look at this. It wants to have the year, the month, and the day, then a t, and then hour, minutes, and second. And this looks feasible, I would say. Looks pretty good to me. And now we can print this and see what's happening. And I think now it is around, it is now lunchtime here in Germany. So it should be around 11 UTC. That's right, 11 UTC. These are UTC times, very important to know. I didn't provide any time zone. So this is the UTC timestamp. And for me now it is actually 1 hour later. So it's 12:15 during noon. Good, we have now the time, and what we need to do now in Spice is we need to convert it into the ephemeris time. Now the ephemeris time is a time that is converting it to the seconds that passed J2000, and we see also the autocompletion understands the context, so we want to convert it by using the UTC to ET function and then use date time now. The good thing about these AI things and also the autocompletion is that sometimes when you write the variables properly, it may already understand the context. And here in our case, it really makes sense. Of course, the print command can be, we can write more things to be a little bit more clear. This is something I also provided in the notebook. So if we execute it, we see here, these are the seconds that passed J2000. So we have everything now in place to compute now the state vector of Earth with respect to the sun. And the state vector, just as a reminder, is the x coordinate, the y coordinate and z coordinate plus the corresponding velocity entries. So a 6-dimensional vector. And the function we will use is spkgeo. And spkgeo returns the state vector, but also the light time. So the seconds I think it is the seconds. Yeah, the seconds. We will take a look at this. The light needs to reach us from the sun. So, but this the distance between the sun and the Earth. Now, in this case, because we will take the sun and Earth as the target and observer. So, let's start. We have the Earth underscore state, I would say, with respect to the sun. Yeah, it's up to you how you name it. Earth, sun, light time. Now, as I said, if you use the auto-completion, the Gemini or so in this case understands more context, which is pretty helpful. But yeah, the SPICE functions are sometimes a little bit too complex for the AI to grasp because there are not a lot of training data available online. Now we need 4 input things. First of all, is the target. The target of the Earth is 399. We will take a look later at these weird numbers. The ephemeris time is ET now, and then we have also the reference frame. It is eclipse J2000. Now this is the reference frame I described to you last time. It is the reference plane where the reference plane is set by the Earth at J2000, so in the year 2000. And so in theory, the Z vector of Earth should be 0, but because of gravitational perturbations, it is not really 0. It's just fluctuating between above and below this reference plane. The observer is the sun itself. It has the number 10. Now, it is not the center of the solar system because the solar system center is the solar system barycenter. I talked about this also last time. And the solar system barycenter, the SSB, has the number 0. So the 0 is the center, the core of the solar system. I would suggest that we print the Earth state vector and also the light time. So let's have a look at this first. Print. Let's see if it understands the context. No, I didn't understand that I want to print both things. We compute it, and there we are. We have like 491 seconds away, light seconds away from the sun. Which makes sense, I would say. Yeah, it is, I think, what was it? Yeah, like 8 minutes or so, roundabout. And here we have the values given in kilometers. So X, Y, Z, and also the corresponding velocities. And you see the number in the Z direction are kind of small compared to the X and Y values. Now, we can maybe compute, first of all, let's take the sun value and also divide it by, let's say, a 60, just to see what the value is. So yeah, 8.89 minutes. All right. I would suggest what we can do also is we can determine the distance between the Earth and the Sun. So what we can do here is we compute now the Earth-Sun distance in kilometers, and we can use NumPy for this. So NumPy has a great function. It's called the norm function, and it's part of the linalg part. So linalg norm. We use the state vector, but we have to be careful because only the first 3 entries are in the distance values. Yeah, the X, Y, Z coordinates. And we start with the 0 counting. So this should consider the 0, the 1 and the 2. And the last value here is not being considered in Python. Now we can put it here, and it should be around 150 million kilometers. So let's have a look. And there we are. We have 3 numbers. 147 million kilometers. So this makes perfectly sense. Okay, I hope I have to be careful. I think I have to scroll up a little bit higher. Otherwise, I will obstruct my own view. But anyway, the question is now, how many astronomical units are there? 147 million. Now, one astronomical unit, as I told you, is a constant, and this value changes because the eccentricity of the Earth is not perfectly 0. But the cool thing is, SPICE has also a function for this. So we can compute the distance in AU by using a SPICyPy function, and this is the convert function. So what we do is we simply take the kilometer value as an input. We provide the input dimensionality is kilometers, and the output dimensionality is AU. Here we want to print this, and now we have winter. And the interesting thing about the winter is that we are closer than 1 AU to the sun. So during winter, Earth is a little bit closer to the sun, and during summer, we are a little bit more far away. Now, you may say, hey, that doesn't make sense really, right? Why is it colder now? Of course, because of the inclination of the Earth itself. This has other, of course, global climatic effects, but let's leave it here as this thing. Now, I would suggest we go and continue with the second part. And in the second part, I would like to talk with you about the Earth's orbital elements. Yeah, so the elements I would like to extract. If you are not 100% familiar with orbital elements, check out my other videos or the last video. In fact, we have 6 orbital elements, and we will consider only 2 of them that are, I would say, good to understand. Now, to determine the orbital elements of the Earth, we need first of all the gravitational parameter of the Sun. Of course, we can take also the SSB, but let's keep it simple with the Sun. And for this, we use the SpicyPy function bot_vrd. And bot_vrd, SpicyPy.bot_vrd, it enables us to extract parameters from different objects, and these parameters, they are stored in this spice function I just downloaded here, this GMDE440TPC. I think there are also the radii of the Earth inside and also the radii of the Sun. I mean, before we extract the gravitational parameter, we can check the radii, and it should return us 3 values. No, the radii are not in there, but I think the GM should be there, the gravitational parameter. Yeah, there it is. So the radii are not stored there. We do not need the first element. We simply need to have the second one. The second one is the gravitational parameter. So let's call it grav mu, and that's how we do it. Now this value here, however, is, I think, an array, so we have to be careful that we need to extract this. So the point why it's being done like this is that if you have radii, then of course you have an array with 3 dimensions, and here it's simply 1 value, but it's not returning it as a float or something, also as a 1-dimensional array. Very good. What we can do now is we can compute now the perihelion, the eccentricity, inclination, and so on of the Earth based by the state vector we computed above. Now, if you did skip the first part, unfortunately, you have to take and consider the code above and execute it, because we need the state vector of the Earth. But it shouldn't worry us too much because it's this very short script. So what we do here, we first compute the Earth underscore pericenter in kilometers. And what we will have is a tuple. So let's do it like this. And then the second entry will be the Earth eccentricity. And the function I use is called as Oscald. Yeah, Oscald is a function that where you put a state vector, you get orbital elements, and the function conics is this vice versa. You put in orbital elements and you get the state vector, which is pretty cool. So here we get the inclination. Inclinations are provided by SPICE in radians, so be careful with the radians degree confusion. Then the next entry is the longitude of ascending node. Let's call it longitude esc, and also in radians. And I like to put also the dimensionality a little bit here because, because then you are not confused what we have. And now we see here also the suggestion of the AI, but I would like to have my own convention. I also prepared everything right, so shouldn't surprise you. The argp, argument of periapsis in radians, and then we have also the mean, but we will not take a look at this, the corresponding time, and mu itself, so the gravitational parameter, it's also being returned. And here you see it is already suggesting us the Oscald function. That's right, that's really cool. And we need the Earth state with respect to the Sun vector. We need the current time, ET now, and the gravitational parameter, grav mu. Execute it, and we have it. And now we can, for example, have a look at the eccentricity. As I said, it shouldn't be 0. It's a little bit eccentric. It's 0.017, so it's almost a perfect circle. Almost. So what do we want to do in this script today. Now, my suggestion is that we will, well, compute something like the how or if the orbital elements change over time. So is the eccentricity, for example, changing? Is the inclination changing? Small spoiler, it is. And these kind of gravitational perturbations, they are computed in SPICE. They are in there. So we can really have a look at it. And I have to be careful. I see myself obstructing it again, so I apologize for that. So I would suggest we will have something like a start date where we want to compute the our computations, and an end date. Let's start with 2025, the 1st January, and the end is maybe 2026, the 1st January. So we will compute the values for 1 year. And in SPICE, if you do not provide any date, then it's considered to be midnight. And of course also UTC. We compute the days now here, and what we do, we use the NumPy function arrange. So arrange computes like equidistant values, here in this case between the start date and the end date. And of course we need to provide the D type, and here the suggestion is correct. It's the date time 64 brackets D. So, oh, here already I also made a next step. And yeah, the suggestion is also pretty good. We want to have it then afterwards as a string, because then the string is the input for the UTC to ET function to compute the ephemeris time. Now, if we execute it, we see here now all the different strings from the 1st of January to the last day of this year. Perfect. In the next step, what we can do now is we will create a pandas data frame. In this pandas data frame, we will put the dates as a column and then compute the state vector and then the orbital elements for the Earth. So elements underscore df equals pandas data frame. And then we have the computational days is one column, and the columns simply call it date. It's a good suggestion. And oh, it already suggested to make the ephemeris time, but let's skip it for now. Just have a look how this looks like, and this is our data frame, 365 rows. Perfect. What we want to do now is we want to compute the ephemeris time, the corresponding ephemeris time for each date to have the ephemeris time. And what we do this, and how do we do this in pandas, is we simply use the log function. And we want to compute all the rows ET, and this is equal to elements df date. So we take the date, each date entry, and we can of course make a vectorized computation, but here I would like to make it row by row to explain it a little bit easier for you. So what we do is we apply the lambda function, and for each entry, so lambda x, so x is like basically the date, and we apply x in the function spicypy.utc to et, and that way we should have the elements df with all the ephemeris times. So let's have a look. Looks perfect. We have here all our ephemeris time, and from there on we can continue working and compute the state vector. Now for this, I would suggest we are simply copy pasting here some things just to make things a little bit easier. Just let's copy the entire thing so I don't have to write down everything on my own. We write down here Earth state, and to compute the Earth state, we will of course to apply something per ephemeris time. And of course, we don't need UTC to ET. We need ET as an input. So we have here spicypy.spkgeo, as we did before. The target is 399. The ephemeris time is x, because we are here using lambda x, and x is the cells entry row-wise, which is the ephemeris time. We have the reference frame that is ecliptic J2000. And of course, we have the observer, and the observer is the sun. Very well. Let me just check I have, of course, everything here. I have my code, of course, right? I mean, it won't surprise you, I assume. And here we have now our pandas data frame with all the state vectors. Cool. Now I would like to compute the orbital elements, and for the orbital elements we need, of course, the columns. I would suggest to just copy paste this here, and what we will do is quick and dirty. We write down some column names. The column names are equal to a list, and the list is just this one here. We just need to quickly make them as strings. I know there are easier ways and faster ways than doing this, but I want to do the lazy way now. So yeah, this looks almost good. And here we are. Yeah, maybe just splitting it up a little bit. Okay, the column names. And now I want to create all these columns with the osgeld function. How do we do that? For this, we take the elements underscore df, and we take the column names. So we want to create the column names, and this is equal to list comprehension, basically. So we can also use the apply part, but I'd use now here this comprehension to show you different ways how to do it. So spicypie.osgeld is the way we need to do. And we take the state vector and the ephemeris time and the gravitational parameter mu. So state, ET, and grav mu. Now it's really complaining about the state and the ET because it's not defined yet. But as I told you, it's a list comprehension. So we have to make a for loop for state and ET. Yeah, this looks good. In zip elements Earth state and Earth's element ET. And this looks like a reasonable autocompletion, to be honest. Yeah, so what it does, but I think there is like the brackets are missing to close it. Yeah. So what it does is it takes the Earth state and the ephemeris time and put this here in the osgeld function, and then, yeah, writing down the entries column-wise. Now we have a small error. I have to just check my code first for state and ET and zip elements state ET and the brackets. Of course, these things happen from time to time. Even in the live coding session, we make these mistakes. Now let me just go quickly back to see where the problem is. And I see the problem here, because here we have the state vector, but as I showed you before, we are computing the state vector and the light time. So what we need to do here is we have to only extract the state vector and ignore the light time. The light time is the second entry, the state vector is the first. So let's recompute it. It still looks the same, right? Now it should work. Yeah, perfect. So now we don't have an error because, yeah, it didn't expect the format it was provided to. So this is our final data frame. We have here the Earth's eccentricity, the inclination and radiance, and so on. Very well. Now I would like to go and see how everything changes in an interactive plot. And for this, we are going to do what you can here use also this part here. I think Colab has also some kind of functionalities to plot things, but I would suggest we print these things. We want to print the eccentricity versus the inclination and then have some kind of interactive slider to see how it changes for every day during the entire year. Now, first of all, let's have an x coordinate. And what we will use is we will use the inclination, and we first of all we need to convert it to degrees. So we have elements underscore df, and there we have Earth inclination radians, and y is not degrees. That doesn't make sense. We will simply use the eccentricity. Okay, no mistake, perfect. And now we need also the number of elements, so let's take nx. Afterwards we need to stack them together, so I could have done this actually in the data frame itself, but yeah, it doesn't really matter. So let's put it here. We have the data of the entire, we call it the path data. So the line we will follow later. So let's do it with the column stack. Oh, very confusing to write these things down here. And I think we have everything now for the preparation. Now in Plotly, we need first of all to define a frame. Yeah, so frame is the first part. Then we need to define the figure and also the sliders and then also the plot itself. But my suggestion is, instead of simply writing these things down, this is the case where I would simply make a copy paste, because to be honest, you can learn a lot of things when you program the data frames and stuff like that. But for plotting routines and everything, my suggestion is always to play around with stuff, right? Because in Plotly, how you start is you begin with a very simple plot. Yeah, so you create something to see if it's working, and then you add more and more features. You update the layout and so on. And now it doesn't make sense to provide line by line the code of the Plotly routine, because the line of thought, the thought process, is already merged in the final version, right? So I don't want to mimic some kind of thought process, because this would be a little bit ridiculous and a waste of time. So I would suggest I'm switching back to my code. I copy paste it and put it here inside. Okay, now I copy and pasted everything now here in this notebook cell, so it should be working. Now in Colab, you need to remove the argument that it's in the notebook, otherwise it will not execute. So here figure show is simply figure show, and if we execute this, I already did, then we will have the plot. Now, before I show it to you here, these two settings, these are important for you. If you have a different resolution and the plot is too small or too big, just adjust here the resolution of the plot accordingly. Now, what we see here is now the inclination in degrees versus the eccentricity. And this is like the position on the beginning of the year, and how the orbital elements of Earth change during the year. So it makes like a very almost hypnotic shape, and you see looks very chaotic and also random. And it's due to the different gravitational perturbations that we have, that are being, so the gravitational perturbation on the Earth, based on the gravitational pull of Jupiter and Saturn and also the other players in the solar system. And this leads to these different changes. It's pretty interesting to see the variation during the year. And you have now all the tools to, for example, download the kernels and see how it behaves in the very, very long run. Like, for example, over the next centuries or so. Okay, this is the conclusion of this part. Now, very quickly, what we can do also is we can, for example, compute the Earth's orbital speed. Yeah, Earth's orbital speed. Now, if you may wondering, okay, why am I sometimes using the word velocity and sometimes speed? I don't think I'm very persistent in this regard, but the thing is, the velocity is always a vector, like x, y, z or something like that. Yeah, so it is also, it provides you a speed direction also. So in which direction is something moving with what velocity. Now the speed is something like the absolute value. Like, for example, in the speedometer in the car, you see like, I don't know, 50 kilometers an hour or so. This is like the speed, but it doesn't provide you any directional information. Yeah, this is basically the difference. And here in this part, I would like to compute the orbital speed and compare it with the theoretical expectation. Now, first of all, what we can do is we compute, of course, the orbital speed with respect to the Sun by using, again, np linalg.norm, and then also the Earth state with respect to the Sun. And now we need the last three entries, so 3, 4, 5, and so on. Well, 3, 3, 4, 5, basically. And then we can also print this value and see how fast Earth is revolving around the Sun in a sun-centric coordinate system in ecliptic J2000, and it's around 30 0.26 kilometers per second. Pretty fast, I would say. And now the question is, what is the theoretical expectation? And for this, we can first create a small lambda function. So some orbital function. And here we use the simply lambda. We don't need to define our own function. We need the gravitational parameter and also the radius. And it's pretty simple to compute. It's basically the square root of gm divided by r. Now, what we do now is we compute now here the theoretical expectation. The naming is a little bit too long. I'm sorry for that. Let's put it like this, but I want it to be very, very crystal clear and not name it 5 or something like that. And now the Colab sees what I want to do. We use v orb func, that's right, gravitational mu. Wait, am I covering it again? Oh man, I'm sorry. Gravitational mu and then Earth-Sun distance in kilometers. Looks good to me. And we can simply print it, but I need, of course, to have the theoretical values. So let's close it. And we have 30.02. Of course, it's not 100% perfect. And of course, this equation assumes a circular orbit. We are almost on a circular orbit, and this explains a little bit the deviation between theory and reality. So let's go to the next part of our coding session. Now we have to talk about the vernal equinox. Think about the Earth at the vernal equinox, where the day and the night have the same length. It's around end of March and end of September. And yeah, in spring, in March around, end of March, the Z vector is pointing perpendicular to the ecliptic plane. And the X vector is pointing towards the Sun, as seen from the Earth. Now, if we move this coordinate system now to the Sun, this leads us to the conclusion that the coordinate of the Earth at the point of the vernal equinox in AU is -1, 0, 0. Yeah, because the X vector again points to the Sun, as seen from the Earth. Now we move the coordinate system along the X-axis to the Sun, and the 0, 0 point is now within the Sun. The X vector is still pointing away from the vernal equinox, more to the direction of autumn. So now I would like to find the exact time when we have the vernal equinox. Not only when, but also what are the exact coordinates. As I said, it will probably be something like -1, 0, 0. For this, we are going to take a look at a certain function called, I have to check it out, it is GFPOSC, the geometric finder function. And this geometric finder function requires some miscellaneous inputs. And instead of just writing down the function, let's think about more the logic, what we will need. What we want to do is we want to target Earth, and we want to observe Earth at a certain, or we want to find the time range when certain geometric conditions are met, namely the vernal equinox. So something like the Earth is at a position of -1, 0, 0, or let's say round about this value. We can also find both equinox points when we are thinking about what does it mean for the other geometric values. Like for example, the y coordinate has to be 0 at both times, right? At one point we have x is +1, on the other hand -1, but y should always be 0 or close to 0. So we will take a look at the times where we have both points. We will do this in a reference frame, namely in ecliptic J2000. This is the thing we want to do. And if you have checked my last video, we have something like correction values considering the light time. But here we just want to take a look at the geometric as is state. So no correction regarding the light, the speed of light. Our observer will be the Sun. So we want to see the vector as seen from the Sun. The function that we have a look at requires also the coordinate system. Yeah, you can compute these things in rectangular or spherical coordinates. For example, in our case, we want to compute everything in rectangular coordinates, so x, y, z. and the coordinate we want to search for, or with certain conditions, will be y. Now, what do we want to achieve? Well, y has to relate to a certain expectation. The relation is equal, yeah? And what do we want to have? We want to have something like a value of 0. The cool thing about the geometric finder is that it allows us to define the time range of certain events. So for example, the function allows us, for example, also to see when we have a close flyby with a satellite and an asteroid. So for example, we don't know what will be the closest point. We can just estimate, maybe it will be, yeah, let's maybe compute the value if it's like plus minus 10% or 5,000 kilometers or what have you. And this adjustment value, we can also set this one here. I will put it to 0. Yeah, I mean, we could theoretically see, we can also say, okay, we want to have the values of y plus minus, I don't know, 50,000 kilometers, but we are pretty sure that the Earth will have a y value of 0 at some point. And the step size allows us to compute the steps at which the geometric finder is searching for it. Yeah, so for example, 86,400 is an entire day. This is of course not very sufficient, yeah, but here for the sake of computation, let's keep it very simple. You can adjust this value accordingly. So we are not finished yet because we need a starting and an end point of the ephemeris time. So first of all, I would suggest we take SpicyPy string to et. This is also a function, so we don't have to take the, we can simply write down a string. And we have here, for example, the 1st of January this year. And I would suggest as the end date, we take the first day of 2026. Now, the thing is that Spice has certain routines we have to define. And one of these is the cnFind function, something like, how you say, the search window where we want to have a look at. So yeah, it is basically the part of the Spice logic itself. So there's like no way to argue about this. It is like the expectation, and maybe also, yeah, like a remnant from older times, because we have also to adjust the value, how many values we want to store in, how many values we want to store in the memory. Of course, nowadays, these things, they are not a problem at all. But yeah, we have to define them anyway. So let me just quickly do this here. The function is what was it? WNINSD. And then we set the starting and end date, and also the cFind. There we are. This value. Good to go. And then also we need to define the value, not the value, the parameter where everything will be stored. It's called simply result. And it's also from utils support type. It is also a Spice double cell. Oh, this autocompletion is a little bit messed up currently. 100, and these are the values we need now to call our actual function, namely SpicyPy.gfposc, and there we have to add the target. Oh, I made a typo. The target, the reference frame, the correction value, that is none. I just have to write down from the top to the bottom. So the observer part, we have the coordinate system. Autocompletion is now not working here. We have the coordinate, the y coordinate we want to search for, namely related equal to 0. We don't need any adjustments. It's basically 0 itself. Now the step size and also the number of values we want to store, I can say 1,000 or 100,000. Nowadays, it really doesn't matter, except you have maybe a Raspberry Pi or so. Then the frame window and also the result itself. Now, if we execute everything, the geometric finder hopefully found something. And the question is, how many events did Spice find where the condition is met that y is equal to 0? We can simply determine it by returning the counts. So count is equal to spicypi dot wn card result, and then we can simply result, yeah. And then we can simply print the count value and see that we have hopefully 2. Yeah, we have 2 values. My head is not obstructing it, good. And we see that we have 2 events, most likely the vernal equinox and the point in autumn. Now what we can do is we can iterate through the results. So we say, okay, we want to go through the count. For loop is maybe an overkill here, but imagine that you are working, for example, with something where you have a lot of flybys also, then a for loop makes sense. And spicypi, now we have a function called spicypi dot wnfetd. We put the result in there and also the entry, the first entry and then the second. And this function provides us 2 time values where the beginning and end part of this, of this event, of this first geometric event occur. Of course, we have here most likely both values will have the same value, but if you want to handle it correctly, you have to still extract them. We can maybe print left and right simply to see what's happening. So let's do it. And we have an invalid syntax because I forgot the in. And we have here the same result. So this is like for the first event and for the second event. So yeah, it doesn't matter if we take the left or the right value, but maybe for the sake of being really not really sure, but if you want to reuse it later on for other stuff, we can, for example, take left plus right divided by 2. So this is the ephemeris time. And we want to compute the corresponding UTC time. And for this, we use, again, spicypi et to UTC. So we see this looks kind of good. And let's have a look. And there we are. We have here the 20th of March and the 23rd of September. Again, the step size is not very good. You can adjust this, of course, to make it more precise. In the next step, what we can do is we can say, okay, we want to simply have a look at the point where the x value is larger than 0. So probably the one at autumn. And for the state vector, here you see also this is now a mistake because it tells us not to print the vernal equinox, but it isn't because it's the point where we have autumn. And autumn, should be a negative value, should be positive, and the spring should be negative, right? So this is already a mistake here by the autocompletion. But before we compute the state, we have, of course, to consider the state, we have to compute the state, of course, by using spicypi.spk position with the target, with the ephemeris time that has been found, with the reference frame, and then also with the correction value that is currently none and the observer. So the state vector is 0. And now what we can do is we can, for example, simply print the values like here, the state 0, state 1, and state 2 that correspond to the x, y, and z values. So let me just print this out quickly. Could have done this more elegantly, but yeah, I think it's okay. So here for the September date, we have these coordinates, and you see y is almost very close to 0, and the z value is -600 kilometers with respect to the ecliptic plane. So the ecliptic plane is still inside the Earth, so to speak. What we can do now is we can also recompute this in AU. So what we can do is we divide this by 1 AU, 1 AU, and 1 AU. And how can we obtain this 1 AU? I would suggest before we compute this for loop, we have 1 AU is equal to spicypi.convert. We want to convert 1 AU to 1 kilometer, because then we divide it and then it will be AU. So let's print it out, and we see here x is 1. Perfect. We achieved now this vernal equinox topic, although we computed the time for autumn. Let's go with the next section, and I would like to talk now more about the kernels we are working with, because now you have a little bit of a feeling what kind of functions are there. We have also some geometric finders and so on, pretty nice, and also only a fraction of what's possible. Now in the next part I would like to show you how kernels are being handled. And first of all, let's see what happens when we clear the kernel. I mean, we can remove all the kernels that have been loaded. So if you're sometimes unaware how many kernels you have, or you have a little bit of chaos, you can still always make this K clear topic thingy. Because now if we, for example, let me just copy paste this one here, and just to be sure, let's really write this down, like 300, and let's maybe take SPK geo. The target is like this. We take ET is equal to ET now that we defined the top. The reference frame is ecliptic J2000, and the observer OBS is the number 10, which corresponds to the sun. You will see that we have an error because nothing has been loaded. Not very surprising, but good to know that these things really exist. Now what I would like to show you is about these values here, 399 and 10 and so on. Now how do we know where these things are coming from? Well, in fact, there is like the web page with the NIF codes on the documentation, but we can also use the kernels themselves to see what kind of values we have in the kernels and to what human readable string they correspond. So what we will do now is we will take a single kernel path. Yeah, so only one, I would say for now. We take the kernels /spk /de432s.bsp, so I don't take any glob or so, and we can compute the IDs or extract the IDs that are in this kernel. Yeah, so you can do this with any kernel, and unfortunately, but we have to work again with this spice cell thingy. So spicypy. No, that's right? Yeah. spicypy.utils.supporttypes.spice integer cell, because we extract simply integers like 0, 300, 399 and so on, what have you, just an artificial size. And then we can extract the values. So spicypy.spk object kernel path comma IDs. And now we can iterate through these IDs and see what is going on. So what do we have here? Let me just make a quick check if there's no error. No, perfect. So we can now go through all the body IDs that are in there. So for body IDs in IDs, we will now extract the different names. So the name is equal to spicypy dot, also here, this is a mistake. It's called bot C2N. I said C, not N to N. Bot C2N. Simply the body ID. And now, oh come on, this is messed up. Things happen. Small little mistakes happen. It's like an ID, not the IDs. So we can now here print, for example, like an F string, for example, what we can do. So we can say name corresponds to the NIF ID, body ID. Oopsie, body ID. And there we are. We have like all the different body IDs, like the Mercury barycenter is 1, Venus barycenter 2, and so on. We have here the Sun with 10, and we have also the Mercury, Venus, Moon, and Earth with also their IDs. Now other planets are of course missing, like Saturn, Jupiter, and so on. We have for them only the barycenter, but there are more kernels that provide the data accordingly, which is pretty nice, I would say. I would suggest that we also now clear the kernels here as well. So we make clear kernel, because in the next step I would like to use the NIF leap second kernel. So let's go with spicypy.fernch So we have to load the kernel here, and it's kernels/lsk nif0012.tls. So let's see if this works. This works perfectly. And now we can compute the ranges where that are defined in the SPK kernel. Now let's do this here. I have to just make a quick check because it is possible that no, it's fine. I have to just reload the kernel. Why did I do this in my documentary? It doesn't make sense to clear the kernel, but well, yeah, sometimes you just have to work on the code and then see that your thought of process was maybe not that 100% clear. Okay, so we can still reuse everything like the IDs. So let's do it. I think I know why. I think I copy pasted it and then duplicated the cell, and then I had this double clearing. So yeah, it's sometimes good to see the thought process while working on it, but you know, I will not redo the entire video now. This would drive me nuts. Let's go with SpicyPy SPK object. So this is also the kernel path there. And then we go through the body ID, 4 IDs. And then what we can do is we extract again the name with spicypy.botc2n body ID. And then we can check what time range is being covered by the SPK kernel. Very well. First of all, we need to, of course, again, to define some kind of window. And we do this by writing down cover. We need to have, again, these kind of, spice support type cell. And I think spice double we use again, just write any number here. And then also spicypy.spkcov, so SPK coverage. What did we have here before? We had SPK object, no, SPK bot C2N. Yeah, we have to sometimes really learn about all these different functions and have a look at it. As I said, there are like hundreds of them, and I also don't know all of them. Sometimes you just execute a certain, how you say it? Yeah, certain algorithm in your head, and you just work with that. Interesting, it is really filling up the function correctly. So the kernel path, the body ID, and the cover, that's right. And then we have to define a card now with double spicypy.wn card cover. Okay, I hope this is correct. No, here's a mistake. It is a for loop, for blah 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 in something. Yeah. Very well. Okay, now we can extract the start ephemeris time and the end ephemeris time with the function wnfetd that we also used before. Now, the good thing is that we can extract the first interval. So I would suggest let's see what's happening. Let's say we have here x and y. Let's call it x and y simply. spicypy.wnfetd cover 0, and let's print just x and y. We get all the different coverages. So this is like a lot, yeah. And it all defines basically the same time range, and this time range is defined in the kernel description AA_summaries that we had already in that we were showing, that I was showing last time. Now I don't want to finish now the entire function here. We can simply write spicypy et to UTC, and then for example take this value and then ISO C, 3, and then we see 1949 13th of December. And if we now can take the last value here, it's basically the same, right? No, it's not the same, but with a plus sign, we have 2050. And these values correspond to the AA summaries that we were talking last time in the video. So this is the way how we find the coverage, so you don't have to really download the files and read the documentary and think, oh, okay, what is now the perfect time range? When do I get an error? You can simply use these kind of for loops to extract the information from the kernels to continue working with it, preventing any manual input, because this manual input, the manual constants, that they will lead to errors. Am I covering it? No, perfect. So I would say we go and jump now to the next part. Very well, we join now the next part of our session, namely we want to create a sky map. So something that you may know from Stellarium or so. We want to have a small sky map where we see where the planets are. And first of all, I would like to have also a planet like Saturn. I don't want to have the barycenter, I want to have Saturn. So we have to download another kernel. So I will do this here in parallel. The link is also here, the code is in the description. And of course, we have to consider one thing for sky maps, namely we need to correct the position of the appearance. Why? Because let's take this example of Saturn and Earth. The shortest distance between both planets is around 9 AU, which corresponds to roughly 80 minutes of light time. Now in this 80 minutes of light time, Saturn is moving as well as Earth is moving. It's not a lot, and also maybe for a small hobby telescope, it's also not a lot. But if you consider a high precision pointing with a telescope, with a radio dish, for example, to track some spacecraft, this can become a problem. Now in our case, first of all, I would suggest before I make a sky map that we create something, a small function to determine if our what is the difference between the geometric state vector of Saturn and the corrected one. So let me first extract the or load in all the kernels first. So as always, kernels, I have to sit a little bit better, kernels slash asterisk, and then spicypy.furnish kernel file paths. We can load the kernels. And now I want to do the following. I want to observe something. I have a target. I want to observe Saturn. And I have I'm a certain observer. I am the Earth. And our reference frame is ecliptic J 2000. Now I'm messing, a little bit too nervous maybe. Eclipse J 2000. Well, this was difficult. Now, first of all, I want to compute the geometric position. Yeah, I don't need the light time, and we can do this with spicypy.spk position. We have a certain target at a certain time with a certain reference frame with no correction and an observer. Now we do the same thing for the apparent position. Now position underscore app target, but here we have to make the correction LT plus S. In the next step, we can use spice again. We can compute the separation between these two vectors by using spicypy dot. And first of all, of course, there is like this very simple maths algebra, right? So linear algebra, you can do vector angle computations. It really is no problem at all. But here we see, oh, the AI knows the context. We want to have a separation of both vectors and compute it in degrees. And what do we have in degrees? Let's have a look. 0.00169 degrees. I wouldn't say that this is really human readable. And I added a small code in my in the online script, so we don't have to. Yeah, I wouldn't suggest to go through there now. Just to give you a rough number, this value here corresponds around to 6 arc seconds. Now that's not a lot for a hobby telescope. It really doesn't matter, but for high precision radio dishes, it's maybe more of an issue. So I would say, without further ado, we are now taking a look at the sky map. So what can we do? What do we want to do now? We want to compute, and I just checked my resources here. We compute the position of the Sun, Venus, Moon, and Mars. You can also do it with Saturn and add more and more if you like. What we will do, we will compute the positions of these these objects, the direction, compute the longitude and the latitude in ecliptic coordinates, convert them in a plot, let's say in a plot way, and then display it. Now, I would suggest we do everything in a pandas data frame. So let's call it sol system df is equal to pd.data frame. And there we have, first of all, sol sys underscore df dot log. And first we need the ephemeris time. And there we take the ET now. Very well, this one first, and then we take the next one also with UTC. So we can also take the UTC, and this is here the date time now. So we have like, yeah, this thing. It's not black magic, is it? I want to add also something like a dictionary for our different objects, and let's do it like this maybe with the Sun, which is 10. We have Venus, that is 299. We have our natural satellite, the Moon, that is 301. We have also Mars with 4. Now here, this is the barycenter. Here we have the coordinates of Mars because in our kernel we do not have all the values present. But it shouldn't bother us too much because now we go through all the body IDs and compute the position, the longitude and the latitude in ecliptic coordinates. So let's do this. We iterate through the dictionary. So for body name in sol, I made a mistake. I want to have sol sys, sol system, sol sys dictionary. First of all, I think I will copy paste this one here because I needed it a few times. We will first create a new column, and this column is basically the direction with respect to Earth in ecliptic coordinates. So let's make an F string here first because we have the directory of body name underscore with respect to Earth in ecliptic coordinates. Now this will be a long line, so where was, oh wait a second, where was the backslash? There was a backslash. So this is the thing we want to compute. So what we need to do, we have to take the ephemeris time and make also again the apply function. Yeah, so we want to apply something here. I mean, it's only one single entry. Maybe it's an overkill, but this is also like a small boilerplate code for you to play around. So if you want to compute the positions for 500 different timestamps or so, you can still reuse the code you see here. So lambda x, and then we need another function to compute it, and it's called spk ezp. The target, we have a target. The target is sol sys dictionary, namely the entry of our current for loop state, so to speak. Make here a comma. Then we have the ephemeris time, that is x, because we iterate through this, but here in our case is only one example, right? We have the reference frame. And the question is, yeah, we can do it in, let's do 2 ways, I would suggest. Okay, first we take the frame, so the ecliptic, and then the app correction. Let's also be 100% correct, LT plus S, and then also the observer, that is 399. And we need here the function returns several values, and we want to have the very first one. Now, let me see, yeah, it works perfectly. So now what we can do is we can use the sol sys value here and extract the longitude and the latitude values. Yeah, so we go here and we compute the longitude radiant eclipsed, long red ecliptic is equal to solstice df. We need, of course, this very crazy naming convention we introduced just a second ago. And, oh, maybe just one word, right? Some people will say, yeah, you did everything with AI or what have you. You can check my old code. It's not like I had AI back then. So this is really good old heritage code. Though I still use AI for my work. I mean, it's not like I'm complaining. It's really helpful. But I think in Spice sometimes there could be some improvements. It's not that 100% correct and good, so to speak. Now what we use here is now we have we computed the the direction vector. So it's like a vector that points into a certain direction. This is the entry we have in row 3. And we need to convert this directional vector into the spherical coordinates. And for this, we use the regrad function. And the first entry, so the second entry here, is the longitude, and the second is the latitude. So what we can do is we simply make here a copy paste, and just be careful that we are not messing around. So we have here not the longitude but the latitude, and we have here the value 2. This is a little bit chaotic, isn't it? It could be worse. It could always be worse. If you are starting with programming, just be aware of one thing, that if you are working together with 5 other coders, they have 5 better options than you have, and also from their perspective. It's not like there's always a good ground truth or common ground. It depends also on the character. Some people really think they know it way better than everybody else. Can be difficult at some point. I mean, I'm a pragmatic coder. It's maybe not the most efficient one sometimes, but it gets the job done. Well, what do we have to do now is something more complicated, and I think the next parts I will simply copy paste, yeah, because first of all I have to convert the longitude values into a very weird way for matplotlib, because I want to have this Skymap. The point is a little bit that the longitude values for matplotlib, they are defined from -180 degrees to +180 degrees, but our values go from 0 to 360. So we have to work with the modulus and clip all the values larger than 180 back to -180 to 0. Now I could just write down here everything, but I would suggest this is one of my code parts I have now since an eternity, since my bachelor thesis even. So this code part is, how old is it now? Geez, 13 years. That's insane. And I would simply suggest to copy paste it, and also the plotting routine. Let me just check. Yeah, it's simply matplotlib code where you just have to adjust all the beautiful settings and so on. And this is also for you maybe to find things out. So let me just switch back in a second. Okay, I'm back, and I just made a small mistake. I removed the direction prefix because it's not a direction, it's like really spherical coordinates. So you have to re-execute this cell here. This is the part that I use with all the modulus thingy. Actually, you can really understand how these things go. Just take a look at it, and you will see what kind of dark magic is happening. However, maybe just a small explanation. I mean, what happens here is, like, if we have values larger than 180, then the modulus is being applied, and it leads to the fact that it's going, the pi is being removed, so to speak. Yeah. But then afterwards we have to also subtract it and put this value negative. Yeah. If the x value is larger than 180 degrees. Yeah. So this is how it's being handled in matplotlib. So I'm not the inventor of it. This is unfortunately a fact we have to deal with. And here we have our plot routine now. I mean, we can quickly go through it. First of all, the most important thing in any plot is the dark background. And then also the projection, an ITOF projection. Yeah, so in spherical coordinates, you have different projection, like the Hammer ITOF, the ITOF, or the Mercator projection, and so on. We want to have a title with the date time. We want to have some different colors for our objects, like for example, yellow for the sun, orange for Venus, gray for our moon, and red for Mars. Then we iterate through all the body objects, add them in the plot, and then also we have to redefine the text. Yeah, so that we want to replace the values along the x-axis with the hour angle, maybe in ecliptic coordinates. That is not correct. I wrote here already equatorial because the final result will be in equatorial coordinates. Just give me 1 second. But first of all, this is our results in ecliptic coordinates. Everything is more or less around the ecliptic plane, more or less, as I said, especially the planets, not the moon. And if we reiterate everything here from frame to, let's say, J2000, so this will also be the final result. Also the naming, just let me go through here first. We see here is the sun, and Venus and Mars are very close to the sun. And I would suggest let's switch quickly to Stellarium to see if it's correct or not. Opened up now Stellarium, so here we have the sun, and you see also it's not lunchtime anymore. I made the video during lunchtime and then just continued working on my university projects and other things, and then I'm rejoining here the video. Anyway, I would suggest we want to have this kind of visualization to see if this is correct. Mars on the left hand side, Venus on the right hand side. Sun is at around 17 hours, 17:30 plus minus, and it's around minus 22 degrees roughly. So just keep this picture in mind. Let's remove the ground and the atmosphere. Let's add the equatorial grid, and let's switch to the equatorial coordinate system. We are then going to the sky field options, where we can go down to the Hammer ITOF projection. Then we have to search for the 0 line. Where is 0? There is 0, and 0 degrees is... I could have done also, yeah, color them, but yeah, anyway, here's 0, so let's zoom out. And here we are with Sun, Saturn, and Venus. Looks what we just computed. And also the Sun is at 17 hours 31, and it's around minus 23 degrees, which makes perfectly sense, I would say. Yeah, corresponds to this one here, but it's not ecliptic J2000, it's now J2000. If you don't know the differences also here, I would kindly ask to check the last video. Now the very last section, and this one is super cool. We are talking about comet Churyumov-Gerasimenko in 3D. Now, if you have not seen a picture of it, I would strongly suggest you. It's like everybody said it's a rubber duck comet. It has these two bodies that are linked together. And if you don't know how it looks like, don't worry, we will take a look at this together. But first of all, we need to download the 3D model itself. Also here, the link and the part are in the description. We need to download them, and what it is I would suggest that we are simply having a look at this so that you know what's going on, and also where the limitations are of these kind of things. Now, I think I want to simply copy paste the file name, this object file name, and then let me just read it. So comet 67p underscore shape object. So the shape is in this thing. So pandas.read CSV. We have this DSKey path. Delimiter white space is true, but I think it will be replaced. I think the delimiter white space will be removed, I think, in the future, but I'm not 100% sure. And then we have also the names. I already know the names, and just follow me. Just follow me. We'll take a look at this just in a moment. Yeah, so we have the type. We have simply x1, simply x2, and surprisingly x3. And then we can have a look at the comet shape. together. Now what do we see here? We have two different types, phi and f. Now, how is a 3D object being created? It is like a big bunch of vectors. The vectors, or the vertices with the v, they give us coordinates of the different dots. Yeah, so it's like you can imagine like a cloud of dots that creates these a cloud of dots that creates this object. However, they're just dots. They're just not it's not like a surface or something. And for this, we have the faces, f. And the faces, it looks like a float, but it's actually an integer. They link the index from the different vectors together. So they say, so this says the index 12,200 and 11,000 and so on. These three vertices, they create a face. So you see me here, one vector, another vector, and this vector, so three, and they together create this triangle shape. And this is called a face. So the three dots are the vertices, and the plane they encapsulate is the face. Now there are different faces with different objects with different resolutions. I have to admit I'm not 100% sure with this K024. I think it means that we have either I think we have 24,000 vertices, and I think there are even of Triumph of Gerasimenko with millions. Yeah? But you have to be aware that this is computational heavy, especially in 3D. So just be careful with that. What we need to do for plotting everything is we need to extract the vertices and the faces first. And most importantly, the faces of the index faces, they start at 1. So we have to subtract 1. Yeah, so let me quickly do this. We have vertices is equal to, and I think we can simply copy paste this data frame so we don't have to write this down all the time. So we make simply loc. Yeah, so we want to locate something, and we want to locate a certain type. And this certain type is the vertex, and it's called with the v, like this. What do we want to extract? We want to extract the x1, x2, and x3 values, especially, as I said, as values. So we have to write it down like this, and then to a list. Yeah, so we have to work with lists, unfortunately. We do the same thing with the faces. We can simply copy paste this part here. We have now faces is equal to equals f. Two faces. I think this looks good. But yeah, we're not converting it to list now, because what we need to do is we have to say faces is faces minus 1. So this is like what we do with in NumPy. NumPy knows what to do. And then we can convert this also as an S type, as integer, because you see we have here the float. We convert it simply to integer. And then at the end, we can then convert it to a list. Dot to list. Perfect. Now we have the lists with the two lists with vertices and also with the integers. And what happens now is I just see my code now. I have a function to plot the routines with Plotly. And also it doesn't really make sense to write all the code. So my suggestion here is as well, let me just copy paste the code from Plotly and we take a look at this comet together. And I'm back and I'm copy pasting the 68 lines of code. Also here with the resolution, just find for width and height and you can adjust the resolution accordingly. Let's execute it simply. Hopefully we have a green tick. Yeah, perfect. And here we have the 3D model of Churyumov-Gerasimenko in kilometers. So it's the actual size of it with the coordinate system. And it's pretty cool. You can also adjust the sun if you like, or something like that, also with Spice. And this is how the comet looks like. So this is where we landed several years ago. Yeah, you can improve it a little bit, maybe the illumination and so on. And I think when we were working at the Philae lander, I think landed somewhere here and was hopping then on the surface, as far as I remember. So yeah, this is how it looks like. And with a higher resolution, of course, you get way more details than in this very smooth object. You see also the bottom is super, super smooth. And that's because this part here was covered in the shadow. Yeah, so the problem was a little bit that we were not able to determine the shapes, the correct shapes here, because it was so covered in the shadows that it was not easy to distinguish any features in the night part of this comet. Now, Rosetta is on the comet. The comet is flying away. It was a great project I was working on. It was a cool time. Anyway, regarding the SPICE overview, I hope you learned something. I hope you enjoyed it as well. And I would suggest we can maybe create larger lectures and also coding sessions with SPICE, but maybe in a few months or so when I'm prepared with more coding stuff for my students in the university and then also here for the YouTube channel. Until then, thank you for watching, stay curious, and see you next time.